So the reason that we're going to talk about graphs is because they're everywhere in Rosetta. They're everywhere in Rosetta because they're a very convenient way of talking about relationships between objects. So where are they? So in describing the chemical composition, say, of a residue type, there's a chemical connectivity graph. There's relationships between, say, pairs of things like atoms, and their relationships like the presence of a chemical bond between them. And that defines a graph. And we use that graph to figure out, for any two atoms within a residue, how many chemical edges separate them. That's how many chemical bonds separate any pair of atoms. And this we use in calculating the Leonard-Jones energy, right? You don't calculate the repulsive force between a pair of atoms that are separated by two bonds, right? Those would just be in collision all the time, and it would just mess up our energy calculations. So those are considered off limits. So that kind of calculation requires, under the hood, graph algorithms for determining what is adjacent to what, how far apart are any two atoms. In representing the kinematics of a molecule, we have a fold tree and an atom tree. Trees are special classes of graphs. I'll talk about trees in some detail in this lecture. For scoring, we have a number of graphs, including the energy graph, which is used to hold the inter-residue energies. So between a pair of residues, what is the energy that you just calculated for them? And that gets stored in the energy graph. There are context graphs, like the 10A neighbor graph, which just answers for every residue from its C beta, how many other residues C betas are within 10 angstroms of it. And you represent that by having edges in graphs. And you count the number of edges between every vertex and or every vertex representing a single residue. In neighbor detection, you want to figure out, given a collection of points scattered in space and some sort of interaction radius, who are the neighbors? And that we use this point graph class. For some of the scoring terms, we use graph algorithms. For instance, the sheet term figures out how many strands are in a sort of contiguous sheet, and that's a graph algorithm. In the packer, we have an interaction graph. We have several for representing vertices, and then edges hold large tables of pair interaction energies. In minimization, there's now a minimization graph, which is a lot like the energy graph. It holds data representing some of the details of each, so residue pair interactions. We won't talk about that very much. In the library structure, if you wanted to just think broadly about what libraries are allowed to depend on each other and what libraries are not allowed to depend on each other, you would look at the library dependency graph. You would have edges between pairs of libraries if one pound included something from another library. We have a lot of compile time issues, which some of you have had a little experience with. And a lot of this has to do with the pound inclusion graph. That is, there's too many files depend on each other. And the more pound inclusions we have, the longer it takes to build Rosetta. And now you have some appreciation for why that's a kind of a big deal. Okay, so formally, what is a graph? A graph is a set of vertices and edges. The vertex set is a set of things, we call them vertices. And the edge set is a set of pairs of vertices. And each pair is called an edge. So an example of this would be, if I can find the laser pointer. So here's a very simple graph. So there's three vertices, U, V, and W. And then I would have the vertex set would be U, V, and W. And then the edge set for this graph would be the pair UV and the pair VW. And you would draw that by putting lines between the vertices and for every pair that you have in your edge set. This is a very simple graph. Graphs are a very powerful way to model problems and then to come up with solutions. So for instance, if you wanted to color each state on a map of the US a different color, You might want to figure out what color you should assign to each state. You might also be curious, just how many crayons can you get away with? How few can you have in order to color every state a different color so that no two neighboring states have the same color? One way to represent that problem is by thinking of each state as a vertex, and then if any state is adjacent to another state, if they share a border, then you would have an edge between the two vertices. So here's a set of vertices, one for each state, and I didn't bother with the northeast because you wouldn't be able to see the relationships here. But then if you have a border between them, then you would get an edge. And you can see, for instance, that Washington and Montana don't have an edge because Idaho is right in the way. And this would be one way of representing sort of the problem of how do you assign colors to the graph. So you would assign a color to each vertex, and then you would make sure that if a pair of vertices have an edge, that they aren't assigned to the same color. Incidentally, it works out. You can prove that for any planar graph like this, you can get away with 4 crayons. You don't need any more than 4 colors to color the graph without any two adjacent vertices having the same color.
Have you ever done that with Europe?
I have not. Yeah, but there is an algorithm. Yeah, so Joe has done it with Europe. He found it challenging.
Can you 7?
No, it's 4. There's the theorem.
What if one place has neighbors with like 7 places?
But they're not all neighbors with each other. So you can go around the color wheel. Like Luxembourg is like right in the center of a whole bunch of things, right?
Yeah.
But its neighbors aren't all adjacent to each other. It's not like not everyone is bordering everyone else. Okay, so another way you can think about graphs is that they're a way to represent predicate logic. So predicate logic is this idea like you've got some statement, some predicate like is the father of, let's say, or what's another possible predicate? Is the father of is fine, because I've got the letter F in front of me, and so that's all I'm going to be able to come up with. So you could say, if this were your truth table, this is all the relationships between 3 objects, u, v, and w, and you wanted to represent the fact that f of u and v is true, and f of v and w is true, but f of u and w is false, then you could create a graph to represent this exactly, right? So you'd have edges in your graph that represent the truth statements, and then the absence of edges to represent falsehoods. So I mean, this is a good way to represent, say, family trees. You can represent the fact that one node in the graph is descended directly from another node in the graph. Okay, so I told you I'd talk a fair amount about trees. So trees are a class of graphs that are very useful for a lot of things. There are several different ways that you can define what it is to be a tree. So one very simple way to describe a tree is that if you count the number of vertices, so these lines here mean the size of the vertex set, and the number of edges. If you count both of these, and the number of vertices is 1 more than the number of edges, and the fact that the graph is connected, then you have a tree. So you can figure out if it's a tree just based on whether you can, say, get between any pair of vertices and then knowing how many vertices and edges there are. A tree, or a graph is a tree if there's one and only one path between any 2 nodes. That is, if you try to go from this node to that node, then you could only get to it by going in a certain flow from one to the other. There's not multiple ways to get between 2 vertices. Another definition is if the vertex set is one larger than the edge set and there are no cycles. A cycle is where you start at one position and you walk along edges without repeating any edges, and you get back to where you started. I'll talk about that a little bit more. Final definition, and this is probably not exhaustive, is that the graph is connected and that there are no cycles. So I guess and if you're out looking for like a tree detection algorithm, you only have to implement a few of these combinations, and then you're guaranteed to get trees. In Rosetta, we have, say, an atom tree. This is a tree where each vertex represents an atom, and each edge represents not a chemical bond, but rather the direction in which you would propagate kinematic changes. That is, one atom would propagate changes directly to another atom, and that would be represented by an edge in the atom tree. There's a full tree as well, which is sort of the residue level version of this. We're going to talk about this extensively today, and this evening's lab will be focused on the full tree. You can define a forest to be a graph where each connected component is a tree. So this graph wouldn't be fully connected, but within each connected component you would have, say, no cycles. You'd have no way of getting between any two vertices with more than one path. Okay, so what is a connected component? So this comes up quite a lot. So it would be the subset of nodes in the graph S where there exists a path between all pairs of vertices between any pair U or V that's in S. All right, so intuitively, like this whole thing is a connected component, because I can get between this vertex and that vertex by walking along a set of edges until I'm there. And I can do that for every pair of vertices in this graph. Okay, so a common problem is if you're given a graph to find the connected component, there are a number of different algorithms, including, say, transitive closure and union find. Let's talk about some of those. Okay, so the first is, what is the solution to this problem? So if someone were to say, this is the solution to my problem, how would you know that they were right? Or what would that solution, what form would it take? So it might be, say, an n by n table where row I and row j represent whether vertex I and j are in the same connected component. Maybe it's some function that you give it the pair I and j and it returns true if they're in the same connected component, false otherwise. If you have, say, then the question might be, what's the representation that you're going to take of your graph? Like, how do you actually write down the graph? How would you state the problem? One way to do it would be to write down an n by n table, n being the number of vertices in the graph. And in each row I and column j would represent, would have a value 1 if there's an edge between I and j. And so you could do this with a symmetric table, or you could just do the upper diagonal, or sorry, the upper triangle of this table. You could represent it in some other way, maybe an integer representing the size of the vertex set, and then a list of integer pairs representing edges. So you just say that every vertex is going to be represented by some index. So there are 50 edges, then you would talk about, 50 nodes, 50 vertices, then you could talk about the edge between vertex 23 and 33. That would be just one of the pairs that you would list in this edge list representation. You could do something a little more fancy where you have a class, and that's the node class, and then each node would have like a list of pointers to edge objects. And so you could have, so that would have it so that each node points to, like if you have a pair of nodes, I and j, and they're adjacent, they have an edge between them, then they would both point in their edge lists to the same edge object. And this edge object might also know that it's the edge between I and j. That's, I guess we have a couple different versions of graphs. In Rosetta, this is one that I'll talk about a little bit more later in the talk. Okay, so let's talk about the matrix representation for graphs, because this is a fairly intuitive one of how you would go about doing it. So this is one way of writing down the connectivity of this graph here. So there are 5 nodes, and then if I look in this table for the edges that are present, so if this is this is the edge between vertex 1 and vertex 3. Then in the first column and the third row, I'd have a 1. And then the first row and the third column, I'd also have a 1. And you can see that this is a symmetric table about the diagonal. And there's like a line of edges right there. Okay, so how can we figure out what the connected components are? One strategy would be to start traversing edges, and then just write down as we go, where we started from and then where we got. So if this is the table. M here is effectively the table of Mi and J's. It's like, if I start at node I, can I get to node J traversing a single edge? And that would be, say, M1 of I and J. M2 would be, can I get to node J walking across 2 edges, right? And this would be, say, a different Boolean table. And then I could continue computing these until I got to M sub n of I and J, which is whether I can get to J starting from I, traversing n edges in the graph. And then if I had all of these tables, then I could just sort of OR them together. I can get between I and J, if I can get there, taking any number of steps. And it's going to take at most n steps, because there are only n possible edges in the graph that I would need to follow. Okay, so an actual implementation of the algorithm would look like this. So in the outer loop, I'm going to have the number of, what am I doing here? Okay, so this is the adjacency table, and then this is, I believe, the, what am I looking at here? 1, 4, 1, 3. This is M12. Okay, so I'm going to compute in this step the connectivity if I start at any vertex and I traverse 2 edges. Can I get to any other vertex? And so I'll look at all of my edges, all my vertices I, and then I'm going to try to get to vertex J, and so let's see, I'll ask, is J reachable from I? And I'll say that that's false, and then I'll iterate probably going to be the number of you're asking steps that I can take. Can I get to where I say, I'm sorry, can I get from I to J by stopping at this intermediate vertex K that they're both reachable through? And so M is maybe the current adjacency table. Sorry, this is the original adjacency table. So I and K have to be adjacent. And then M prime is some representation of whether I can get to J from vertex K in some number of steps, in some countable number of steps. And then if that's true, then if this dual condition is true, then I'll say that J is reachable from I, taking, if this is, let's say the M2 array, then this would be the combination of the M1 array and the the M2 table, and this would be the combination of the M2 table and the M table. So that would be 3 steps where you could get to J from I in 3 steps. And so you would write that down. M double prime would then be the next letter. So this would be M3 IJ, that you can get to J from I in 3 steps. So you could do this a number of times, I guess keeping track or creating a new M prime and a new double prime each iteration through this loop. Yes.
So effectively then you will not have n tables, but you will have a larger number than n, because then you can always replace the parts, and you have so many more number of steps.
Right. You're not committing yourself to having returned to where you started. You're just saying, right, so what the question was, if you're allowing yourself to go backwards. If node 1 can traverse this edge to 3 and then end up back at itself in 2 steps, then it could take a lot longer than n steps to get to any vertex in the graph. So that's not quite what's going on here, because I'll say that it's reachable for me to get to vertex 1 from vertex 1 in 2 steps. But it's also reachable for me to get to vertex 4 in 2 steps. And so I'll write down both in position 1, 1 and position 1, 4 that I can get there. And so if I were to continue heading off and say just a long trail of, if I had just a linear graph, right? So it's node 1, 2, 3, 4, 5, 6, 7, 8, and I needed to get down here in some number of steps, actually make forward progress, even though I'm also kind of going backwards as time progresses as well. Yeah, so the graph, it's not an efficient, like you're basically searching kind of in all directions at once, right? You're not taking a step and then stepping backwards and then taking a step and then stepping backwards. You're instead taking like a multitude of steps in all directions and they multiply. All right, so maybe a more efficient version of this would be, so the most efficient version of this is the union find algorithm. I'm going to present that. The question might be phrased in a different way. So like you could say each vertex can be represented by a group index. And if we can build up an index of which group, if I can figure out quickly if I'm in the same group as someone else, then we can figure out maybe more quickly who all the groups are. Okay, so the idea here is that you're going to have for each vertex a group leader, a representative of that group, and each vertex is going to say state the index of its group representative, and we start off with this array. So position 1 is going to say I'm my own representative. Position 2 says I'm my own representative, and so forth. And then we're going to update this table as we progress through this algorithm. So what it's going to basically be is that we're going to iterate across each edge in the graph. And each edge that we see, we're going to ask whether the representative of U is the same as the representative of V. If they're not, then we're going to perform a union on these 2 nodes. We're going to somehow write down that these 2 nodes are in the same group. And then this will propagate, this change will propagate to the rest of the group members, like the groups that U and V were already a part of. Okay, so this find algorithm is given a particular node and a pointer to the representatives array, which is this array here. You ask, is the representative for this node itself? If so, then return the representative. Otherwise, figure out who the representative is for this vertex by recursing. And then change the representative for this node to that new value. And then return that representative. So we're going to sort of update this representatives list as we traverse the graph. So for each edge, we're going to call find twice, and so we're going to be updating the representatives possibly twice for every vertex in a group until we find our way to the representative for that vertex. So so that's the find subroutine. The union subroutine is if I and j are given vertex indices I and vertex index j, and then there's representative set. Go ahead and set the representative for j to be the representative for I. And I just did a little shorthand here because I was running out of space when I was preparing this. But there's no extra function rep I. Or maybe this is supposed to be find. That's what I did. This is supposed to be find. Okay, so this is not perfectly the union find algorithm. There's a few more subtleties to it, but it's mostly there. So let's walk through it for this case. So for this graph, let's first start on this edge 1, 3. Okay, so we're going to ask for this. Who's the representative for U? Who's the representative for V? And then we'll see if they're the same. So this algorithm, as we walk through this, we'll see that the representative for 1 is 1, so that's 1. And we'll see that the representative for 3 is 3, so they're not the same. So we're going to perform a union on these two nodes, U and V. And then this works out just that the representative for vertex 3 becomes 1. So we've updated the representative array. All right, so we're going to look at the next edge, say between 2 and 5. And we're going to ask who is the representative for 2, and that's 2, and who's the representative for 5, and it's 5. And so we're going to update, we're going to perform a union on 2 and 5. So that's going to update the representative for 5 to now become 2. So the representative for 5 is 2. It's clear, is it clear to everyone that the index for each vertex is now the index into this array? So that the 5th position in the array is what's getting updated when I talk about vertex 5. Is everybody comfortable with that? Okay. Okay, and so the last one, the last edge in this graph is 3 and 4. And so that will mean asking who is a representative for 3. So you go to this array. Is the representative for 3 3? And the answer is no, because the representative for position 3 is 1. So we're going to recurse. And so we'll find the representative for 1, and that will be 1. So we recursed on the representative for position 3, and that's 1. And that will bring us here, and the representative for 1 is 1, and so we return 1. And so the representatives array for 3 now popping off the stack is going to be set again to 1, so it doesn't really change, and then we'll return 1. So we'll compare the representative of 1 here against the representative of 4. I'm sorry, so this representative of 3 is 1. We'll compare 1 against the representative of 4, so we'll have to compute this. So representative of 4 is 4, and so now we find out that the representatives for 3 and 4 are not the same, so they're in separate groups right now. And so we're going to update, we're going to perform a union, and we'll update the representative list for position 4, and we'll say it's 1. All right, so now what we have is an array that represents the group representative of each vertex in the graph. And you can see that positions 1, 3, and 4 all have the same representative. And positions 2 and 5 both have the same representative. And so if you're asking, if you're given any pair of vertices, you can answer quickly whether they're in the same connected component by just looking at who their representative is. So you can look up into this array very quickly. You can say, 3 and 4 are in the same connected component because they both have the same representative, the representative of 1. So this is actually useful. This is used constantly within Rosetta on BOINC as people run ab initio in the form of the sheet score, right? So in the sheet score, we just have this, this penalty for strands to be just by themselves hanging out in space. Strands want to be part of sheets. And so you start off, if you have just one strand hanging out by itself, you have a penalty of 1.87. I don't know exactly how these numbers were computed, but they're like the poker hand version of strand probability formation, or sheet probability formation. So that's just a quote from the paper that I remember reading about it, and I don't remember anything else. Okay, so if you have 2 strands, then the penalty is much less severe. Strangely, there seems to be an increase in the penalty for having 3 strands in a sheet. That confuses me. But if you get to 4 or more strands, then you have a fairly low penalty of just 0.17. And so there's sort of an implicit penalty against having strands at all. I guess Rosetta is much happier for you to form helices. But you know, I mean, your fragments are going to bias where you're going to search through secondary structure space. But as long as you have strands, then you may as well make large sheets out of them. So it favors the formation of sheets and penalizes strands just hanging out by themselves. And so you might reasonably ask, how would you go about calculating this score? And the way I've re-implemented it is to model each strand as a node in a graph. And then if you have a list of strand pairings, that is strand 5 is paired with strand 7, then you can treat that as an edge in the graph and use the union find algorithm to say that now 5 and 7 must belong to the same sheet. So you connect strands into sheets, and then you count the number of strands in each sheet, and you assign a score. Summing up, so you iterate across each strand, and you count the number of other strands in the same sheet with that strand, making sure to count each sheet only once. And then you add up this penalty accordingly, or for each sheet. Okay, so trees don't have cycles. So what is a cycle? It's it's a path where you start from one node, and then you can traverse edges without repeating any edge until you get back to where you started. So in this graph, the path EFGHE is a cycle. And the presence of this cycle in the graph means it's not a tree. I won't count it for you now, but if you were to sit down and count it out, you would see that the number of edges in this graph is equal to the number of vertices. And knowing also that this graph is connected, you could conclude that it's not a tree. There's a flavor of graphs called directed graphs, which are super useful. They're capable of representing an asymmetric relationship, for instance, is a parent of. And when you draw an edge in a directed graph, as opposed to the undirected graphs, which I've just been talking about, use an arrow to indicate the direction in which this relationship flows. In a directed graph, if you talk about a path through a directed graph, you talk about a path that only traverses edges in a single direction. So this is clearly a tree in directed of a directed graph, and here's the root. So this is the vertex from which all other vertices are descended. If you wanted to talk about cycles in a directed graph, you could start here and you could traverse, starting from the blunt end to the sharp end of the edge, and doing that until you get back to where you started. And that would be a full cycle. And so that's a cycle in the directed graph. This is not a cycle. So if you start at this vertex, you can't get back to where you started. You can't traverse this edge in this direction if you start at the blunt and go to the sharp edge. And you can't do that for any other vertex. So this vertex can't go anywhere. This vertex can go here, but can't go anywhere else. And this vertex can only go here. So it's got more edges or it's got as many edges as it has vertices, but it's acyclic in a certain way. And so we talk about directed acyclic graphs quite a bit, and this is an example of a directed acyclic graph. It doesn't have a cycle, even though it's not a tree in the traditional sense, right? So DAGs, these are directed graphs that do not contain cycles. There are a lot of algorithms and a lot of problems for which a DAG representation is very useful. For instance, this is how I make spaghetti. So I start off, and I've got all these steps, and each step takes some amount of time. So I need to chop onions. I'm slow, and so it takes me quite a long time. Once I chop the onions, I have to saute them, and that takes forever. Meanwhile, I need to get the pan ready in order to chop the onions, and the pan heats up relatively quickly compared to how slow I am. I need to chop the sausage. That doesn't take very long, or that takes a little bit of time, not quite as bad as the onions. Sausage needs to saute for quite some time to get cooked. I need to fill a big pot of water up. That doesn't take too long, but it takes a really long time for that to come to a boil. And then once I add the boil, I guess I overcooked my spaghetti. Maybe this should be 6 minutes. I'll apologize. Okay, so, and then back up here, let's say once I've got the onions and the sausage sauteed, then I need to add spices. And once I've added the spices, then I need to add the sauce, which I just pre-buy because I'm that kind of person. And then reduce it for quite some time until it's nice and blended, and then I'm done. And so one question you might ask for this is, what should I do, like how should I schedule the process of cooking dinner so that it gets cooked as quickly as possible? What tasks should I do first? And one way of looking at it is thinking about the critical path. The critical path is the set of tasks where if any task along that path falls behind, then the whole project is delayed. Vertices that are not on the critical path, they can be delayed without delaying the whole project. There's some give in their scheduling. So for instance, it's pretty fast to get the spaghetti cooked, like in the scale of things. Like if I have to spend all this time chopping and sauteing onions, I can do basically the whole process of cooking the spaghetti while that happens. So in this graph, the critical path is the sauce reduction, the adding of spices, the sauteing of onions, and the chopping of onions. And so if anything delays this process, then the whole meal is slower. You can calculate the critical path using, well, I wrote it down and I've already forgotten. Sorry, it's right here. The backflow algorithm. I don't know why I can't remember that. Okay. So in that algorithm, you kind of work from the end and you work backwards and you figure out just how long you have until you get from any vertex to the end. And then you get your way all the way back to the start, and then you can figure out how far it is from the start to the end, and then you can figure out if you've written down information along the way of what was your slowest step, then how you go from the start to the end. Okay, so we use DAGs in Rosetta to represent the library dependencies. This is something, this figure you'll see a lot of in the rest of our talks here. So, so top to bottom, we sort of have just a path representation of the library dependencies. So our very lowest level library, objects FCL, there's some functions in utility that depend on it, but objects FCL doesn't depend at all on utility. Numeric depends on utility, but utility does not depend on numeric. Basic depends on numeric and utility and objects FCL, but doesn't depend, none of them depend on basic. So the dependency goes up the graph in this way. That is, core is dependent on basic, but not dependent on protocols. And so if you introduce a dependency between core and devel, for instance, Rosetta won't link at all. Rosetta may compile, but you'll never get an executable out of this, at least for lots of compilers. And so so enforcing the proper pound inclusion, the proper dependencies is important, making sure that we can continue developing in Rosetta. And that's well represented by a graph algorithm. And so we can just use a graph algorithm to not have to scan through all of the pound includes and all of the files to make sure that everything's okay. We instead just have it done mechanically and tell us whether or not the set of dependencies that currently exist meet this dependency requirement. Core is actually composed of 5 sublibraries. They similarly have this linear dependency structure. 2 is allowed to depend on 1, but 1 cannot depend on 2, and so forth. The protocols libraries, protocols used to just be a big block, and we split it up into lots of little blocks. And I'm not drawing all the edges here. I'm just drawing the edges between one level and the next level. So protocols 2A is allowed to depend on protocols 1, and protocols 2B is allowed to depend on protocols 1. Protocols 2A is not allowed to depend on protocols 2B. These are like horses at the track, right? They have blinders on, and so they can't see the horse that's next to them. You can see, I guess, the horse that's out in front. There's a lot of dependency down through here in protocols 3. And then protocols 4 gets quite wide. So protocols 4A is not allowed to depend on protocols 4E, but they're both allowed to depend on protocols 3, and they do. Right, so I think I may have just said all of this out loud. When I say depends on, like, so the directionality of this edge, that means pound including a file from one directory into another. So we organize all of our pound inclusions, all of our dependency relationships based on what directory things live in. We don't have any other way of enforcing that. You might be confused because we have these like protocols.a.4.source.settings, right? If you take a file out of one of the directories listed in there and move it into protocols.e.4.source.settings, right? One of the other lateral protocols libraries in 4, you may think that that's perfectly fine, but if you've just moved where the directory gets compiled, like a subdirectory, then our code will still see that as a library inclusion issue. That is the code that detects the interlibrary dependencies. So we have like the top level libraries of protocols. I think we'll cover this more later, so I won't talk about it too much now. But beneath protocols, for instance, there's the match directory. So match contains a lot of code. If you were to take a subdirectory of match, say match upstream, and move that into protocols.6, I think like that is just say that it gets built as part of protocols.6 as opposed to physically moving the directory. You're not doing an MV, you're just editing these .source.settings files. Then our algorithm for figuring out whether library dependencies are legal or not will get confused. The reason for that is that when you specify in the source.settings file what CC files get built with what libraries, what you're doing there is just saying that the CC file is part of the library, but you're not saying anything about the header file that's associated with or any other headers. And so there's no very easy way to associate header files with particular libraries. And so what we do instead is just associate directories. Okay, so one thing I want to talk about is the difference between sparse and dense graphs. If you have a problem and you're trying to decide on how to represent the graph that's part of that problem, you might want to know something about the relationship of say, the number of vertices in the graph to the number of edges. In sparse graphs, most nodes do not have an edge between them. In dense graphs, most nodes do. So if there are, let's say, n nodes in a graph, then a dense graph might require order n squared space. So the maximum possible number of edges, if you had a fully connected graph, would be n times n minus 1 over 2. This is sort of the number of entries in the upper diagonal of a table, the upper triangle, I should say. If instead you had some constant number of vertices, constant number of edges for each node, then you can use a sparse graph representation. So for instance, if you said that each residue has 40 neighbors, right? I have some idea of how dense a protein can be and how far my score function reaches, so that between any pair of residues, you're just not going to interact if you're further than, say, 12 angstroms apart. Then there's some constant bound on the number of edges that each vertex would have in this neighbor relationship graph. Each residue is a vertex, and each edge being the existence of some non-zero interaction between them. And if that's your problem, then a sparse graph with, say, 20 times the number of nodes edges is the right representation for you. Okay, so how would you go about representing a sparse graph? For a dense graph, you want a table, right? You just have so much data that it makes sense to just allocate space for all of it, and then you can put a 0 or a 1 at each position where you have an edge. But if you have a sparse graph, then there may be a couple different ways that you could go about representing that. So one would be to, say, have a graph that contains a list of index pairs listing the nodes that are part of each edge, right? So, so what do I mean by that? So it's kind of like the way you would formulate the problem as I described earlier, where you say, I have some number of nodes, and then here are all of my edges. So I have 50 nodes, and here's edge 23 to 33. This representation is somewhat problematic because it's hard to look for an edge in particular. Like, is the edge 45, 52 in the graph? I guess it would be 49 or something below my cap of 50, if I'm going to stay consistent. But say you have an edge that you're interested in particular, there's no quick way to find it, right? You just start at the beginning of the list and walk to the end. And if you wanted to know about, say, all of the edges incident on a particular node, that's also problematic in this representation. So if you had, you could have a different representation where you have, say, node objects, say like a class node, and each node in this has an edge list, like a list of pointers to edge objects. So you have edge objects, node objects, and then a list on each edge of its incident, pointers to its incident edges. Then, if you have a sparse graph, then there are only, there's at most like 40 edges incident on any particular node. So you could go to that node and you could look at the maximum of 40 edges in there and pick out the one that you were interested in. So if you were looking for the edge between 45 and 49, then you go to vertex 45 and you scan through its edge list and you see of the 40 edges, is there one to edge 49? And if, so this is big O notation. I'm not sure if everyone here is familiar with this. So if you have something that scales quadratically, you'd say that it's n squared. If you have something that scales linearly, then it would be order n. And if you have something that doesn't depend on the number of nodes in the graph at all, then that would be order 1. It's a constant time cost. So this representation also makes it particularly easy to iterate across all the edges for a single node, right? They're all represented right there on the node object. Okay, so in Rosetta we have class graph. This lives in core. It probably should live in utility. And it has this graph class, it has a node class, and it has an edge class. And you interact primarily through the graph class, but you can access the node and edge classes. And then we have derivatives of it. For instance, in core scoring, the energy graph derives publicly from core graph. The energy node derives publicly from the graph node, and the energy edge derives publicly from the energy edge. In UML, it would look like this, where the energy graph derives from the graph, the energy edge derives from the edge, and the energy node derives from the node. And it's totally fine, in case this was jarring, for a class in one namespace to derive from a class in a different namespace. So these are kind of boxed off into the core scoring namespace and the core graph namespace. It's totally legitimate to derive a class in one namespace from something in a different namespace. Namespacing doesn't prevent inheritance at all. Okay, so what does class graph look like? You initialize a graph by saying how many nodes there are, and then it goes and constructs a whole bunch of nodes. You can ask for a node, so you can say get node. You can ask for an edge where you give the indices of 2 edges, and it will look for it and then return a pointer to it if it exists. You can delete a particular edge. You can ask if an edge exists. You can ask for the total number of edges. You can ask for an iterator to the beginning of the edge list for the graph. Say you just want to walk across every edge in the graph and you don't particularly care what order, then you can ask for the edge list begin and the edge list end. So the graph actually represents its own edge list. I'll come back to this in just a moment, what that means. And then the graph also has a vector of nodes, a vector of vertices. Later this week, we'll talk about what a const version of these two functions means. So just bear that in mind, that sometimes you have access to a constant object and sometimes you don't. And when you have access to a constant object, then you have to use the constant methods. We'll repeat this, go into great detail on that. Okay, so what does graph node, or what does class node look like? Well, it also has an edge list, so it has an incident edge list. And then it's got, the way it represents its edges is that it segregates its edges into edges to lower indexed vertices and edges to higher indexed vertices. And it uses the position of one of the elements in this edge list to represent the boundary between the two. So the first upper edge, that's a pointer to a place in this list where everything beyond it is going to be to an upper vertex, and everything before it in the list is to a lower vertex. And it has a pointer back to the owning graph that it has. And so when the node gets constructed, it gets this pointer, the graph gives it a pointer to itself, and it tells it its index. I guess I'm not giving all the private data here. Each node also knows its own index. And then you can ask for a number of different things. For instance, you can ask for the edge list begin and edge list end. You can ask for the const edge list begin and the const edge list end. This is what you would have to use if you had access to a constant node instead of a non-constant node. You can ask for iterators to the beginning and ending of the edge list representing the lower vertices or edges to lower vertexes, and you can ask for the range of iterators to the upper vertices. And so if you were interested in iterating across all the edges in the graph, where in this iteration you're going to pick the lower vertex and you want to see all other vertices. So you're going to iterate for I equals 1 to the number of nodes. And then for each I want to iterate across all of its edges, but I don't want to see any edge twice. Then you can do that by looking at only the upper edge list, right? You're never going to, if you iterate across the entire edge list for each vertex, then you would end up seeing nodes to, or edges to lower indexed nodes. You would see each edge twice. So if you restrict yourself, when you're looking at I, look at only edges to nodes with index greater than I, then you can visit each edge only once. Class edge, similarly, it has a pointer back to its owner. It has the indices of the two nodes that it's incident upon. It has a pointer to each of those nodes in case you need those. And then it keeps a couple of iterators so that it can abstract itself out of the edge list that it lives inside of very quickly. So when the graph adds an edge, the edge keeps track of where it ended up in the edge lists for its vertices. Each vertex will give it an iterator to where it got inserted into its edge lists. And the edge keeps that so that when you delete this edge, you can pull it out of each of those edge lists without having to iterate across those edge lists to find that edge. So it's a bit faster. If you have a problem where you need to store data on nodes and edges, then one of the solutions for this is to derive from class graph. As an example, the energy graph stores residue pair energies on each edge. The constraint graph stores constraint edges between pairs of residues. What else do I have on this side? Oh, that's it, wow. Yeah, these are just two examples of derivatives of class graph. Class graph does a lot of work in maintaining edge lists and whatnot, and so we avoid code duplication by deriving new classes where the base class does a lot of the work and the new classes just add an extra small layer of complexity on top of it. In this case, the energy graph is a very simple class. It just has a little bit of data on each of the edges and some small amount of data. Actually, it doesn't even store data on its nodes. So it's a very small class. Okay, so class graph is responsible for actually instantiating new nodes and edges, and it does so by using this factory method. So the problem is if you want to add an edge to the energy graph, you want to make sure that it constructs energy edges and energy nodes, as opposed to letting the base class make just regular nodes and edges. And the way it does this is by letting you override these factory methods. So create new node, create new edge, or create new edge with an example of an existing edge. So that's, excuse me just a sec. Class graph, when you add an edge, it invokes this function create new edge, which it provides a version of. It's not an abstract function. But when you derive a new class, you need to override this create new edge. And then once it's created this edge, then it pushes this back into its own edge list, and then it tells that edge to set its position in its, gives it an iterator so that it can keep track of its position in the graph's edge list. There are a few other things that go on kind of behind the scenes here. And so in order for the energy graph to create energy edges, it overrides this method, create new edge, so that it instantiates, it calls new energy edge. It gives a pointer to itself and the N1 and N2, the vertex indices. Okay, so I'm going to conclude here with just a description of the algorithm of how you actually go about rescoring a pose. So you have the pose, it's been scored already. And so there's an energy graph representing the energies that were calculated the last time the score function looked at the pose. But the pose has changed, its structure has changed since the last time the score function looked at it. And so some of those edges are now obsolete. So the algorithm for now recalculating the score of the pose is to iterate across all the edges in the energy graph. And for any pair of edges, figure out if those two residues, the residues that they represent, have moved with respect to each other since the time of the last scoring. So behind the scenes, the atom tree is keeping track of how movement has propagated through the system. It keeps track of where the movements happen, so you can figure out, as movements have propagated, who's changed with respect to someone else. We'll go into this in greater detail this afternoon. And then it will tell you, it will assign a color to each residue in the graph, so that if two residues have the same color, then they have not moved with respect to each other. So if two residues have moved with respect to each other, that means the energies that were stored in this edge, these are now obsolete. They don't represent the current energies in the system. So as an example here of why you don't throw away all the edges, imagine you've got your ab initio structure and it's folding in this direction, and you make a change in the middle of the structure, and that change propagates downstream. All right, so now the interactions between residues here and residues there, they all have to be recalculated. They're no longer accurate. But the energies, say between a residue here and a residue there, they're still good, because these two residues haven't moved with respect to each other, so you don't have to get rid of those energies. You can reuse that previously cached calculation. And similarly, the energies between these two residues, they wouldn't have to be thrown out either, because they haven't moved with respect to each other. Okay, so after you've thrown out all of the old edges, all the ones whose energies need to be recalculated or are no longer accurate, then you go and figure out which pair of residues are near each other. So there's a point graph that's used to find neighbors. And then each node in this graph represents an XYZ coordinate, a point, and you have this distance threshold that you use to figure out whether or not two nodes are close enough that that they would have an edge, that they would interact. And then you put an edge in this point graph for every pair of vertices that satisfy that property. You iterate across this point graph and you add new edges to your energy graph if if you have ij, then you check and see if residues I and j have moved with respect to each other. If they haven't moved with respect to each other, then you already have an edge in the graph, because they would have an edge from the last time you calculated the energies. And if they have moved with respect to each other, let's say, so you've made this fragment insertion. Now this residue is near that residue in the point graph. We've figured out that they're within an interaction distance. So you know that they've moved with respect to each other. So in step one, if they had an edge before, that edge has been dropped. So now it's safe to add a new edge between that pair of residues. So you do that. You add an edge to the energy graph. And then you iterate across the energy graph. And for every edge, you have to rescore a portion of the energy function. But for edges that are connecting residues with two different colors, you know that you have a fresh edge. So then you have to rescore what they're called the context-independent two-body energies. The Leonard-Jones energy is one such term. So you can avoid recalculating the context-independent two-body energies, the Leonard-Jones energies, for example, if two residues have not moved with respect to each other since the last time they were scored. You can skip over that calculation for a particular edge. And then you just, once you've calculated the residue pair energies for edge ij, then you store that pair energy on the edge, and you can look back at it later to know what energy you calculated for it. And that's it. Are there any questions?
Are residue types or residue type sets implemented using DAGs? Because it seems like they're derived from the backbone, an ordering. Say you have a sparse you want to rebuild it because they're missing atoms. Are DAGs used there because they're deriving from these parent atoms?
Conceptually, we don't have an explicit use of DAGs. I guess there's a relationship between, what am I talking about? Yes. So when you're building the coordinate from an atom that's missing, the way it's done, I guess there are a couple different ways that can do it, but the easiest way to do it is to build from the atom tree. So the atom tree describes the internal geometries of how you get to a particular atom, let's call it the fourth atom, based on the distance to the third atom, the angle between the fourth, the third, and the second atom, and then the dihedral between the fourth, the third, the second, and the first atom. And so there's a DAG going from 1 to 2, 2 to 3, and 3 to 4. It's in fact a tree, but all directed trees are DAGs. They're just like a special case of DAGs. There are ways that you can, there's code inside the atom tree so that you don't have to, if you have atoms 2, 3, and 4 and you don't have atom 1, then you can work backwards to figure out how to build atom 1. But the easiest way to do it is to build forward.